Hi, I'm Chen from Zhejiang University. I'm actually excited to present our work here in this video. It's a joint work with ETH Zurich, Baidu Corporation, and University of Technology Sydney. And we are the first place in the third large-scale video object segmentation challenge, referring video object segmentation track. In this work, we try to rethink cross-modal interaction from a top-down perspective. So first, let's take a look at what is referring video object segmentation, or I will brief it as RVOS in later presentation. Given a sequence of video clip and some natural language references, RVOS targets at segmenting video objects referred by the expressions. As shown in the bottom, a person is covered in red and the skateboard is covered in green, corresponding to the descriptions. So, as an intersection area of both visual and linguistic modalities, it's actually challenging, while facing not only comprehensively understanding of the semantics within the individual modalities, but also cross them in pixel level, especially that facing some hard cases like semantically similar instances or inconspicuous reference exist in the same scenarios, and for linguistic domain like facing complex descriptions and so on. So for handling the task, existing methods typically working in a bottom-up fashion, that is, both the intramodal and cross-modal interactions are performed at grade level. Thus, they have no ideas or explicit knowledge about visual objects. However, it deviates to the description logics that we are introducing a scenario where we tend to describe it at instance level. That conflict might directly lead to unreliable cross-modal reasoning and inaccurate segmentations. So, in this work, we try to rethink the task from a top-down perspective. That means we will catch the object-level information first and then comprehensively exploring the cross-modal and cross-object relations for the grounding. So based on such observations, our pipeline is designed as follows. It's quite simple as it should be. The first, an object checklist generation stage is shown in the left column, and a checklist language grounding stage is shown on the right. The figure is organized in clockwise order from left to bottom corner. In the first stage, we generate a set of high-quality object checklists. The object candidates are first generated by applying instance segmentation over several sampled keyframes. Then, a propagation module is applied on the detected candidate masks to propagate the instance to the whole radio sequence in form of checklists. Well, as we sample several keyframes, there exist a lot of similar checklists that correspond to the same instance. Thus, a checklist NMS mechanism is designed to remove the redundant checklists and select the high-quality ones as candidates for the following grounding stage, where we ground the reference over detected checklists and select the best matched one as the final output. And for the detailed implementation, we take HTC for instance segmentation, where it can be replaced with any other existing methods. And we take CVPRW' Plus for instance propagation. Then, I will dive in a little bit on the detailed implementation of checklist NMS and checklist grounding module. So first, for checklist NMS, with all available pairs of checklists, we consider them as the checklists of the same instance if the intersection over union is greater than the threshold, and we only reserve the better one based on the checklist score. That's checklet NMS. And then, for the checklet grounding module, instance-level features are simply concatenated with linguistic features and fed into a transformer for within and cross-modal interaction formulation, while the variable part is cut from the final output and further fed into a multi-layer perceptron for score prediction. We found it surprisingly effective as the self-attention mechanism in the transformer. The interactions among different object checklets and between different modalities are comprehensively captured and leading to promising grounding performance. And then finally, on the final performance, we finally evaluate our approach on RVOS challenge and achieve the best performance on both the two sides across all the metrics and outperformed the second team with a large margin, as in the table. And here, we provide some qualitative results of our proposed methods on the challenge split, while the descriptions are typed in the top and the results are shown in the bottom. It could be observed that our methods can produce the reference with sharp boundaries. Here is a zoom in, and the model can precisely distinguish the instances among different categories, where there is leopard and deer in the video sequence. Now, even while facing some inconspicuous reference, like a nearly unavailable leopard on the left, our model can also segment it out. So here is the final of my presentation, and that's all. And for more details, please refer to the technical report and Chen. Thanks again for watching this video.